This present lecture, we solve a one-dimensional heat equation. Next, we see what is the method of separation of variables. Next, what are steady state solutions. Lastly, we solve a one-dimensional wave equation. Before solving heat equation, let us recall what is a one-dimensional heat equation. Suppose that u equals u of x comma t is a function of two variables x and t, in which x is a space variable and t is a time variable. We suppose that all the partial derivatives of u equals u of x comma t exist and they are all continuous in the domain of u. The one-dimensional heat equation is a second order linear PDE given by u suffix t equals a square u suffix xx. Here u suffix t equals dou u by dou t and u suffix xx equals dou square u by dou x square. The constant a square is called a diffusion constant. This equation u suffix t equals a square uxx can also be written as a square u sub xx minus u sub t equals 0. This one-dimensional heat equation or one-dimensional diffusion equation is a homogeneous linear second order PDE and it is a prototypical example of a large class of equations called parabolic equations. We have derived this one-dimensional heat equation in the previous lecture. Let's solve our one-dimensional heat equation or one-dimensional diffusion equation u sub t equals a square u sub xx. Here u sub t equals dou u by dou t and u sub xx equals dou square u by dou x square. A square is called a diffusion constant. This equation is called one-dimensional only because we have only one space variable x. Now, to solve this one-dimensional heat equation u sub t equals a square u sub xx, we use the method of separation of variables. This method of separation of variables is a very important method and it is widely used to solve many second order linear PDEs. To solve our one-dimensional heat equation, we use this method of separation of variables. Suppose that u of x comma t equals capital X of small x times capital T of small t is a solution of the given one-dimensional diffusion equation u sub t equals a square u sub xx. Here we suppose that u of x comma t equals x of x times t of t. X of x is a function of a single variable small x and capital T of small t is also a function of a single variable t and t represents time here. Since we supposed u of x comma t equals x of x times t of t is a solution of our one-dimensional heat equation, it satisfies the given equation. So let us substitute u equals x of x times t of t in the given equation. Then the given equation becomes dou by dou t of x of x t of t equals a square dou square by dou x square x of x t of t, which implies x of x t dash of t equals a square x double dash of x t of t, because on the left side we differentiated partially with respect to small t. So we have to treat x as a constant and we have to differentiate t. So we get x of x times t dash of t on the LHS. Similarly, on the RHS, we have to differentiate x of x times t of t with respect to x partially twice. We have to treat t as a constant and we have to differentiate x. So we obtain capital X double dash of small x times capital T of small t on the RHS. Hence we obtain x of x times t dash of t equals a square x double dash of x t of t. In this method, we have supposed that u is a product of two functions. One function depends on x only, that is capital X of small x, and the second function depends on time t, that is capital T of small t. We have substituted u equals x of x times t of t in the given equation, and hence we obtained capital X of small x t dash of t equals a square x double dash of x t of t. Now we divide that equation with x of x times t of t on both sides. Then we obtain t dash of t by t of t equals a square x double dash of x by x of x. Here we can observe that all the functions of x are on one side and all the functions of time variable t on the other side. That's why this method is called the method of separation of variables. We separated all the functions of x on one side and all the functions of t on the other side. If we divide with a square also, we obtain 1 by a square capital T dash of t upon capital T of t equals capital X double dash of small x upon capital X of small x. Now we equate this expression to a constant, say lambda. Then we obtain 1 by a square capital T dash of small t upon capital T of small t equals capital X double dash of small x upon capital X of small x equals lambda. From this equation, we can write the following two equations. 1 by a square t dash of t upon t of t equals lambda, and x double dash of x upon x of x equals lambda. These equations can be written as t dash of t equals a square lambda t of t and x double dash of x equals lambda x of x. Now we obtain two ordinary differential equations. The first differential equation is x double dash of x minus lambda x of x equals 0. This is a second order linear homogeneous differential equation with constant coefficients. The next differential equation is capital T dash of t minus a square lambda capital T of t is equal to 0. This is a first order homogeneous linear differential equation with constant coefficients. So, we have obtained two ordinary differential equations. Now we have to solve these two differential equations to obtain the values of capital X of x and capital T of small t. We don't know the nature of the parameter lambda. Our aim is to find out the solution u of x comma t. We have supposed that u of x comma t equals capital X of x times capital T of t in this method. So, if we find out x of x and t of t, we can find out the solution u of x comma t of our one-dimensional heat equation u sub t equals a square u sub xx. In this procedure, we have obtained two ordinary differential equations. The first differential equation is capital X double dash of small x minus lambda capital X of small x equals 0. Our second differential equation is capital T dash of small t minus lambda capital T of t equals 0. We don't know the nature of the number lambda. Depending on the values of lambda, now we divide this problem into three cases. In the first case, suppose that lambda equals 0. If we substitute lambda equals 0 in the first differential equation, x double dash of x minus lambda x of x equals 0, we obtain x double dash of x equals 0. If we integrate this equation on both sides with respect to x, we get integral x double dash of x dx equals some constant c1, which implies capital letter x dash of small x equals c1. If we integrate this x dash of x equals c1 again with respect to x on both sides, we get integral x dash of x dx equals integral C1 dx plus C2, which implies capital X of small x equals C1 small x plus C2. Here C1 and C2 are any two arbitrary constants. So in this case we have found the value of capital X of x. Here capital X of x equals C1x plus C2 in this case. Now let us substitute lambda equals 0 in the next differential equation, capital T dash of t minus lambda a squared t of t equals 0. If we put lambda equals 0, this differential equation becomes capital T dash of small t equals 0. If we integrate this differential equation, capital T dash of t is equal to 0 on both sides, we obtain integral T dash of t dt is equal to C3, where C3 is some integrating constant. From this equation we obtain capital T of small t equals C3, where C3 is an arbitrary constant. So we have found capital X of x equals C1x plus C2 and capital T of t equals C3. Now let us write down the solution u of x comma t in this case. U of x comma t equals the product of x of x and t of t. Substitute the values of x of x and t of t here. Then we obtain u of x comma t equals C1x plus C2 times C3. If we expand the RHS, we obtain u of x comma t equals C1 C3x plus C2 C3. C1 C3 is a constant and C2 C3 is also a constant. We can take C in the place of C1 C3 and D in the place of C2 C3. Then we obtain u of x comma t equals Cx plus D, where C equals C1 C3 and D equals C2 C3. Of course, C and D are also arbitrary constants. In this case, when lambda equals 0, the general solution of the one-dimensional heat equation is u of x comma t equals Cx plus D, where C and D are arbitrary constants. Case 2. In this case 2, we suppose that lambda is positive. Since lambda is positive, we can take lambda equals k square, where k is some real number. Now, since k square is positive, lambda is a positive real number. Let us substitute lambda equals k square in our differential equations. X double dash of x minus lambda x of x equals 0 and t dash of t minus a square lambda t of t equals 0. First let us consider the differential equation x double dash of x minus lambda x of x equals 0. Substitute lambda equals k square in this differential equation. Then we obtain x double dash of x minus k square x of x equals 0. This is a second order linear homogeneous differential equation. The auxiliary equation corresponding to this second order differential equation is m square minus k square equals 0. The factors of this auxiliary equation are m plus k times m minus k equals 0. The roots of this auxiliary equation are m equals k and m equals minus k. We have taken lambda equals k square to obtain m equals k and m equals minus k here. Otherwise, we would have obtained root k here. To avoid square root, we have supposed that lambda equals k square. That gave us m equals k and m equals minus k as roots of this auxiliary equation m square minus k square equals 0. Now the solution of x double dash of x minus k square x of x equals 0 is given by x of x equals e power kx c1 plus c2 e power minus kx. Hence, capital X of x equals c1 e power kx plus c2 e power minus kx. Now, we solve our second differential equation t dash of t minus a square lambda t of t equals 0. Substitute lambda is equal to k square in this differential equation. We obtain t dash of t minus a square k square t of t equals 0. This is a first order differential equation with constant coefficients, and this equation is homogeneous. It can be solved by using variable separable method. From the differential equation t dash of t minus a square k square t of t equals 0, we can write t dash of t equals a square k square t of t, which implies t dash of t by t of t equals a square k square. Integrating on both sides with respect to t, we get integral t dash of t by t of t dt equals a square k square integral dt, which implies log of t of t equals a square k square t plus some constant, say c suffix 3. From this equation, we can write down t of t equals e to the power of a square k square t plus c3. That implies t of t equals e power a square k square t times e power c3. Since c3 is a constant, e power c3 is also a constant. Let's replace e power c3 with some other constant, say c suffix 4. Then we obtain capital T of small t equals c suffix 4 e power a square k square t. So we have found the values of capital X of x and capital T of small t in this case. So in this case, we obtained capital X of x equals c1 e power kx plus c2 e power minus kx, and capital T of small t equals c4 e power a square k square t. The general solution of the given one-dimensional heat equation u sub t equals a square u sub xx equals u of x comma t equals x of x t of t. Substitute the values of x of x and t of t in this equation. Then we obtain u of x comma t equals c1 e power kx plus c2 e power minus kx times c4 e power a square k square t. If we multiply it with c4, we obtain u of x comma t equals c1 c4 e power kx plus c2 c4 e power minus kx times e power a square k square t. Instead of c1 c4, we can take some constant, say c. Instead of c2 c4, we can take some other constant, say d. Then we obtain u of x comma t equals c e power kx plus d e power minus kx times e power a square k square t. Of course, we can further simplify this equation by multiplying everything on the right hand side. So, in this case, when lambda is positive, we have shown that the solution of the given one-dimensional heat equation is u of x comma t equals c e power kx plus d e power minus kx times e power a square k square t. Let's see what happens to the solution in case 3. In this case, we take lambda as a negative quantity. Since lambda is negative or lambda less than 0, we can take lambda equals minus k square for some real number k. Since k is a real number, k square is positive and minus k square is negative. Since lambda equals minus k square, lambda is also negative. We have already completed the case lambda is equal to 0 in case 1. So here lambda not equal to 0. So k is also not equal to 0. Hence lambda equals minus k square and k not equal to 0. So let us substitute the lambda value lambda equals minus k square in the differential equations x double dash of x minus lambda x of x equals 0 and t dash of t minus lambda a square t of t equals 0. Substitute lambda equals minus k square in these differential equations. Then our differential equations take the form x double dash of x plus k square x of x equals 0. Our second differential equation takes the form t dash of t plus a square k square t of t equals 0. First, let's solve the differential equation x double dash of x plus k square x of x equals 0. This is a second order homogeneous differential equation with constant coefficients. The auxiliary equation corresponding to this second order linear differential equation is m square plus k square equals 0. In order to find out the roots of this auxiliary equation m square plus k square equals 0, easily we have selected lambda equals minus k square. Now the roots of this auxiliary equation m square plus k square equals 0 or m equals plus ki and m equals minus ki. Here I square equals minus 1. The roots m equals ki and m equals minus ki are imaginary roots. So the solution of x double dash of x plus k square x of x equals 0 is given by x of x equals c1 cos kx plus c2 sin kx, where c1 and c2 are any two arbitrary constants. We have solved the first differential equation x double dash of x plus k square x of x equals 0, and we obtained x of x equals c1 cos kx plus c2 sin kx. Now let's solve our second differential equation t dash of t plus a square k square t of t equals 0. This is a first order homogeneous linear differential equation. We can solve this first order differential equation by using variable separable method. T dash of t plus a square k square t of t equals 0 can be written as t dash of t equals minus a square k square t of t, which implies t dash of t by t of t equals minus a square k square. Integrating this equation on both sides, we get integral t dash of t by t of t dt equals minus integral a square k square dt, which implies log t of t equals minus a square k square t plus c3, where c3 is an arbitrary constant. This can be written as t of t equals e power minus a square k square t plus c3, which implies t of t equals e power minus a square k square t times e power c3. Since c3 is a constant, e power c3 is another constant. Let's replace this constant e power c3 with some other constant c4. Then we obtain t of t equals c4 e power minus a square k square t. So far we have found the values of x of x and t of t. X of x equals c1 cos kx plus c2 sin kx, and t of t equals c4 e power minus a square k square t. In this case 3, we have to write down the general solution u of x comma t. In this method of separation of variables, we have supposed that u of x comma t is a product of x of x and t of t. That is, u of x comma t equals capital X of small x times capital T of small t. In this case 3, we have found the values of x of x and t of t. We need to substitute their values here. Then the general solution of the given one-dimensional diffusion equation as follows. U of x comma t equals x of x t of t. That implies u of x comma t equals c1 cos kx plus c2 sin kx times c4 e power minus a square k square t. If we multiply with c4 on the RHS, we obtain u of x comma t equals c1 c4 cos kx plus C2 C4 sin kx times e power minus a square k square t. Since C1 C4 and C2 C4 are constants, we can replace them with some other constants, say C and D. Then we can rewrite the solution as follows. U of x comma t equals c cos kx plus d sin kx times e power minus a square k square t. Now we have found the general solutions of our one-dimensional heat equation u sub t equals a square u sub xx in three different cases. In the first case, we have taken lambda equals 0 and we found the solution. In the second case, we have taken lambda greater than 0 and we obtained the general solution. In case 3, we supposed that lambda is negative and we found the general solution. In all these three cases, the solution which we obtained in the third case is mostly used solution. The solution is in case 3 is a very important solution and that solution is widely used. Remember one fact that we have not considered any conditions on the given one-dimensional heat equation u sub t equals a square u sub xx. Without applying any conditions, we have solved the one-dimensional heat equation so far. Remember that previously we have solved the one-dimensional heat equation without considering any conditions. Now let us solve the same one-dimensional heat equation or diffusion equation by taking some boundary conditions. Let us solve it as a problem. In this problem, let's take up our one-dimensional heat equation u sub t equals a square u sub xx, which is the same equation, but here we solve it under a few conditions. The boundary conditions are u of 0 comma t and u of L comma t. Both the conditions are given to be 0. That is, u of 0 comma t equals 0 and u of L comma t equals 0. An initial condition is given to us. That means at a time t equals 0, u of x comma t is some function of x. That means the initial condition is u of x comma 0 equals f of x. But this f of x must coincide with our boundary conditions. So we must take f of 0 equals 0 and f of L equals 0. Then only this function f of x copes up with the given boundary conditions. Now let us solve this boundary value problem. Consider our equation u sub t equals a square u sub xx with the given conditions. Let's see the physical interpretation of the given problem. In this problem, let us take a copper rod which is very thin and with a very small cross section. Its length is say L centimeters. Suppose that it is placed along the x-axis between the positions x equals 0 and x equals L. That means it's a finite copper rod having length L centimeters, which starts at the point x equals 0 and ends at the point x equals L. Suppose that the left end of this copper rod is maintained at 0 degrees centigrade. Similarly, suppose that the right end of this copper rod at the position x equals L is also kept at 0 degrees centigrade. That means both the ends of the copper rod are placed at 0 degrees centigrade. So we maintain cooling at both ends of the copper rod. This copper rod is a good conductor of heat. Suppose that it is properly insulated with some non-conductor. Here, this copper rod is insulated and placed along the x-axis so that the heat flows along the x-axis only. Now, this is the physical interpretation of the given boundary value problem. Now, as usual, we solve our one-dimensional heat equation or diffusion equation by using the same method of separation of variables as we have done previously. The entire procedure is same. Now we have to use our boundary conditions in all the three previous cases. Let us consider case 1. In our case 1, we obtained one general solution previously, which was given by u of x comma t equals cx plus d, where c and d are arbitrary constants. We have seen this solution in the case 1 previously. Now we apply the given boundary conditions to this solution in this case. Our first boundary condition is u of 0 comma t equals 0. To apply this boundary condition, let us plug in x equals 0 in the solution u of x comma t equals cx plus d. If we put x equals 0, we get u of 0 comma t equals c times 0 plus d, which implies u of 0 comma t equals d. But u of 0 comma t is given to be 0. So we obtain d equals 0. Now consider u of x comma t equals cx plus d again. Let's use our next boundary condition u of L comma t equals 0. To apply this boundary condition, put x equals L in the solution u of x comma t equals Cx plus d. Put x equals L. Then it becomes u of L comma t equals Cl plus d. The left hand side u of L comma t is given to be 0. So the left hand side becomes 0. We have already found that d equals 0. Hence, this equation u of L comma t equals Cl plus d becomes Cl equals 0. L is the length of the copper rod. It cannot be 0. So, Cl equals 0 implies C equals 0. So, we have shown that C equals 0 and D equals 0. If we substitute C equals 0 and D equals 0 in the solution, u of x comma t equals Cx plus d, we obtain u of x comma t equals 0. This is a trivial solution. Since u of x comma t equals 0, we do nothing. So the solution is not at all interesting for us. In our present problem, we are solving the one-dimensional heat equation u sub t equals a square u sub xx by using the method of separation of variables. But in this present problem, some boundary conditions and an initial condition are also given. If we use the same method of separation of variables in the three cases, we obtain general solutions. We have seen the first case already. What happens after substituting the boundary conditions? Now let us see the case 2. Let us take the solution in case 2 and we verify what happens if we use our boundary conditions which are given in our present problem. In case 2, when we supposed lambda is positive, we obtain the general solution as u of x comma t equals c1 e power kx plus c2 e power minus kx times c4 e power a square k square t. If we multiply with c4 on the RHS, we get u of x comma t equals c1 c4 e power kx plus c2 c4 e power minus kx times e power a square k square t. This is our solution in case 2. Now let's apply our boundary conditions to this solution. Our first boundary condition is u of 0 comma t equals 0. To apply this boundary condition, put x equals 0 in the solution. Then we obtain u of 0 comma t equals c1 c4 plus c2 c4 times e power a square k square t. Because we have substituted x equals 0, then on the right hand side e power kx and e power minus kx become 1. Hence, u of 0 comma t equals c1 c4 plus c2 c4 times e power a square k square t. But u of 0 comma t is given to be 0. So the LHS becomes 0. Hence we obtain 0 equals C1C4 plus C2C4 times e power a square k square t. From this we can write C1C4 plus C2C4 equals 0. Instead of C1C4, take one constant C, and instead of C2C4, take some constant D. Then this equation becomes C plus D equals 0. That implies D equals minus C. Again, consider our solution u of x comma t equals C1 e power kx plus C2 e power minus kx times C4 e power a square k square t. This time, let's use our second boundary condition u of L comma t equals 0 to apply this boundary condition. Put x equals L in the solution. Then we obtain u of L comma t equals C1 e power kl plus C2 e power minus kl times e power a square k square t times C4. But u of L comma t is given to be 0. If we substitute u of L comma t equals 0, we obtain 0 equals C1 e power kl plus C2 e power minus kl times C4 e power a square k square t. Multiplying with C4 on the RHS, we obtain 0 equals C1 C4 e power kl plus C2 C4 e power minus kl times e power a square k square t. We have supposed that C1 C4 equals C and C2 C4 equals D. Plugging in these two constants here, we obtain 0 equals C e power kl plus D e power minus kl times e power a square k square t. But we have shown that D equals minus C. Substitute D equals minus C in this equation. We obtain 0 equals C e power kl minus C e power minus kl times e power a square k square t. If we take out C outside, we obtain C times e power kl minus e power minus kl times e power a square k square t equals 0. That implies C equals 0 because e to the power of anything cannot be 0. Since D equals minus C and C equals 0, we get D equals 0. Since C equals 0 and D equals 0, all the constants C1, C2, C3 and C4 vanish. All the constants become 0. Then our solution u of x comma t becomes 0. U of x comma t equals 0 is also a trivial solution. In this case, after applying the given boundary conditions, the solution of our one-dimensional heat equation is the trivial solution u of x comma t equals 0. We can't do anything with this solution. So this solution u of x comma t equals 0 is of no use. We have already solved the one-dimensional heat equation or diffusion equation u sub x t equals a square u sub xx by using the method of separation of variables in 3 cases depending on the lambda values. Now we have to take up the case 3 and we need to apply the given boundary conditions to the solution in this present problem. In case 3, if we suppose lambda less than 0, we found that the general solution of the given one-dimensional heat equation is u of x comma t equals c1 cos kx plus c2 sin kx times c4 e power minus a square k square t. Here c1, c2, c3 and c4 are arbitrary constants. If we multiply with c4 on the RHS, we obtain u of x comma t equals c1 c4 cos kx plus c2 c4 sin kx times e power minus a square k square t. Since c1 c4 is a constant, we replace this constant with another constant, say capital A. Similarly, because c2 c4 is a constant, we replace this constant with some another constant, say capital B. Then the solution in this case can be written as u of x comma t equals a cos kx plus b sin kx times e power minus a square k square t. Now we need to apply the given boundary conditions to this solution. Our first boundary condition is u of 0 comma t equals 0. Let's apply this boundary condition to the solution. Put x equals 0. Then we obtain u of 0 comma t equals a cos 0 plus b sin 0 times e power minus a square k square t. Since cos 0 equals 1 and sin 0 equals 0, we obtain u of 0 comma t equals a e power minus a square k square t. But u of 0 comma t equals 0. If we plug in this value u of 0 comma t equals 0, we obtain 0 equals a times e power minus a square k square t. That implies a times e power minus a square k square t equals 0. Since e power minus a square k square t is not equal to 0, we get a equals 0. So we have shown that the first constant a equals 0. Next we apply our second boundary condition u of L comma t equals 0 in the solution. Consider the solution u of x comma t equals a cos kx plus b sin kx times e power minus a square k square t. Put x equals L. Then we get u of L comma t equals a cos kl plus b sin kl times e power minus a square k square t. We know that u of L comma t equals 0 and the constant capital A equals 0. If we substitute these two values here, we obtain 0 equals b sin kl e power minus a square k square t. That implies b sin kl e power minus a square k square t equals 0. If we divide with e power minus a square k square t on both sides, this equation yields us capital B sin kl equals 0. From this equation, we get either b equals 0 or sin kl equals 0. If we suppose b equals 0, then already a equals 0. Now b equals 0. If we substitute a equals 0 and b equals 0 in the solution, we get u of x comma t equals 0, which is a trivial solution and it is of no use. So we should not take b equals 0. So b must be non-zero. B sin kl equals 0 and b not equal to 0 give us sin kl equals 0. Sin kl equals 0 happens only when k equals n pi by l, where n takes the positive integer values. That means n equals 1, 2, 3, so on. So in this case, we have obtained that sin kl equals 0, and from it we got that k takes the values n pi by l for n equals 1, 2, 3, so on. We have already seen that k equals n pi by l and n takes the values 1, 2, 3, so on. We have found that capital A equals 0 and B not equals 0. If we substitute all these values in the solution, we obtain u of x comma t equals capital B sin of n pi x by l e power minus a square k square t. If we put k equals n pi by l, we get u of x comma t equals b sin n pi x by l e power minus a square n square pi square t by l square. Now we need to apply our initial condition u of x comma 0 equals f of x. This function f of x satisfies the conditions f of 0 equals 0 and f of l equals 0. If we apply this initial condition to our solution, we get u of x comma 0 equals b sin n pi x by L. Because if we put t equals 0, e power minus a square k square t equals 1. So we get u of x comma 0 equals b sin n pi x by L. But u of x comma 0 equals f of x. Then this equation becomes f of x equals b sin n pi x by L. From this equation, we can find out b. For each positive integer value of n, we get one constant b, say b suffix n. For n equals 1, we get b1. For n equals 2, we get b2, and so on so forth. So, we can write f of x equals summation sigma n runs from 0 to infinity b suffix n sin n by x by L. This is by the law of superposition. Similarly, our solution takes the form u of x comma t equals summation sigma n runs from 0 to infinity bn sin of n pi x by L e power minus a square n square pi square t by L square. If we observe here, f of x equals summation sigma n equals 0 to infinity bn sin of n pi x by L. This is nothing but the Fourier series of f of x. Actually, this is a Fourier sine series. Joseph Fourier studied the heat equation and he solved the heat equation. He introduced Fourier series to solve the heat equation. Our solution u of x comma t takes the form u of x comma t equals summation sigma n equals 0 to infinity bn sin of n pi x by L e power minus a square k square t for k equals n pi by L. So we have solved the one-dimensional heat equation u sub t equals a square u sub xx by applying the given boundary conditions. Here we must remember one fact. If we apply the given boundary conditions, we can find out the arbitrary constants. So, we have solved the one-dimensional heat equations without using any conditions, and also we have solved one-dimensional heat equation by using boundary conditions in this problem. What are steady state solutions? Steady state solution is also called equilibrium solution. For example, if we heat the metal rod in one dimension for a long time, the conduction of the heat is uniform, then it does not change with the time after a long heating of the rod. Now, let's see what are steady state solutions. Consider our one-dimensional heat equation u sub t equals a square u sub xx. A steady state solution or an equilibrium solution is a solution which does not change with time. I have already mentioned that steady state solution or an equilibrium solution mean it does not change with time. So if we consider our heat equation u sub t equals a square uxx in this equation, because the solution u of x comma t is a steady state solution of the given equation, it does not change as the time proceeds. The change in u with the time is 0 because there is no change with respect to time. So dou u by dou t equals 0, that is u sub t equals 0. If we plug in u sub t equals 0 in the given equation, we obtain ut equals a square uxx implies a square uxx equals 0 because I substituted ut equals 0 on the left hand side. A square uxx equals 0 implies uxx equals 0 because a square is not equal to 0. If a square equals 0, we cannot call the given equation as a one-dimensional heat equation. That's why a square must not be 0. Hence we obtain u sub xx equals 0, which implies dou square u by dou x square equals 0. If we integrate this equation with respect to x twice on both sides, we obtain u of x comma t is equal to cx plus d. This is a steady state solution for the given one-dimensional heat equation. Let's solve a problem on steady state solution. In this problem, we need to find out an equilibrium solution for our one-dimensional heat equation u sub t equals a square u sub xx under the boundary conditions u of 0 comma t equals minus 5 and u of 10 comma t equals 25. Let's solve this problem. Consider our one-dimensional heat equation u sub t equals a square u sub xx. Because we want a steady state solution for this equation, we have to substitute u sub t equals 0. If we put u sub t equals 0, the given one-dimensional equation becomes a square uxx equals 0, which implies u sub xx equals 0. If we integrate it with respect to x on both sides twice, we obtain u of x comma t equals cx plus d, where c and d are arbitrary constants. We have to find out these two arbitrary constants c and d by using the given boundary conditions. The first boundary condition is u of 0 comma t equals minus 5. Let us apply this condition to the solution. Consider u of x comma t equals cx plus d. Put x equals 0. Then we get u of 0 comma t equals c times 0 plus d, which implies u of 0 comma t equals d. But u of 0 comma t equals minus 5. So we get d equals minus 5. So we have found one arbitrary constant d, which equals minus 5. Next we apply the second boundary condition u of 10 comma t equals 25. Again consider u of x comma t equals cx plus d. Put x equals 10. U of 10 comma t equals 10c plus d, but you have 10 comma t equals 25 and d equals minus 5. If we substitute these values here, we obtain 25 equals 10c minus 5, which implies 10c equals 30 and hence c equals 3. So the values of the arbitrary constants are c equals 3 and d equals minus 5. If we substitute these values, the solution of this problem becomes u of x comma t equals 3x minus 5. This is the required steady state solution for the given one-dimensional heat equation under the given boundary conditions. We are done. Now we take up a one-dimensional wave equation. We are going to solve a one-dimensional wave equation given by u sub tt equals a square u sub xx. In this equation, we have only one space variable x and t is the time variable. Because we have only one space variable x, this equation is called a one-dimensional wave equation. We solve this one-dimensional wave equation u sub tt equals a square u sub xx by using the method of separation of variables. This one-dimensional wave equation is also a homogeneous second order linear PDE. This one-dimensional wave equation can also be written as a square u sub xx minus u sub tt equals 0. We have already seen that this equation is a prototypical example of a large class of equations called hyperbolic equations. Let us solve this equation by using the method of separation of variables without considering any conditions. Remember, we are not applying any conditions on this equation. Let us suppose that u of x comma t equals capital X of small x times capital T of small t is a solution of the given one-dimensional heat equation u sub tt equals a square u sub xx. Since we have supposed that u of x comma t equals x of x times t of t, a solution of the given equation, it must satisfy the given equation. So we need to substitute u of x comma t equals x of x times t of t in the wave equation u sub tt equals a square u sub xx. Then it becomes dou square by dou t square x of x t of t equals a square dou square by dou x square x of x t of t. On the left side, we have to differentiate t of t twice with respect to t by treating x as a constant. On the right hand side, we have to differentiate x twice partially with respect to x by treating t as a constant. Then we get x of x t double dash of t equals a square x double dash of x t of t. If we write all the x terms on one side and all the t terms on the other side, we obtain t double dash of t by t of t equals a square x double dash of x by x of x. If we divide this equation with a square on both sides again, we get 1 by a square t double dash of t by t of t equals x double dash of x by x of x. We can equate this equation to a parameter, say lambda. Then we obtain 1 by a square t double dash of t by t of t equals x double dash of x by x of x equals lambda. We must remember one fact that a square not equal to 0. If a square equals 0, the given equation u sub tt equals a square u sub xx cannot be called a one-dimensional wave equation. So, a square is not equal to 0. From 1 by a square t double dash of t by t of t equals x double dash of x by x of x equals lambda, we obtain two second order linear differential equations as follows. The first second order linear differential equation is x double dash of x minus lambda x of x equals 0. This equation is obtained by equating x double dash of x by x of x to lambda. If we take 1 by a square t double dash of t by t of t equals lambda, we obtain the second differential equation of the form t double dash of t minus a square lambda t of t equals 0. Thus, our partial differential equation gives us two second order linear differential equations with constant coefficients. We solve these two equations and we obtain x of x and t of t. By using them, we write the general solution u of x comma t. Depending on the values of lambda, we divide the problem into three cases. In the first case, we suppose that lambda equals 0. Now we have to substitute this lambda equals 0 in the two differential equations x double dash of x minus lambda x of x equals 0 and t double dash of t minus a square lambda t of t equals 0. If we substitute lambda equals 0 in the first differential equation x double dash of x minus lambda x of x equals 0, we obtain x double dash of x is equal to 0. If we integrate this with respect to x on both sides, we get integral x double dash of x dx is equal to c1, where c1 is a constant. This implies x dash of x equals c1. If we integrate with respect to x on both sides again, we get integral x dash of x dx equals integral c1 dx plus c2. That implies x of x equals c1x plus c2, where c1 and c2 are arbitrary constants. Now we substitute lambda equals 0 in the second differential equation t double dash of t minus a square lambda t of t equals 0, which implies t double dash of t equals 0. If we integrate this equation with respect to t on both sides, we get integral t double dash of t dt equals c3, which implies t dash of t equals c3, where c3 is a constant. If we integrate again with respect to t on both sides, we get integral t dash of t dt equals integral c3 dt plus c4, which implies t of t equals c3t plus c4. Now we have found the values of x of x and t of t. In this case, x of x equals c1x plus c2 and t of t equals c3t plus c4. If we substitute the values of x of x and t of t in the general solution, u of x comma t equals x of x times t of t, we obtain u of x comma t equals c1 x plus c2 times c3t plus c4. If we multiply on the RHS, we get u of x comma t equals c1 c3 xt plus c1 c4 x plus c2 c3 t plus c2 c4. If we replace the constants with some other constants a, b, c, d, we get u of x comma t equals a xt plus b x plus c t plus d. This is a general solution of the one-dimensional wave equation in the case lambda equals 0. In case 2, we suppose that lambda is positive. Since lambda greater than 0, we can take lambda equals k square for some real number k. We substitute lambda equals k square in our first differential equation x double dash of x minus lambda x of x equals 0. Then it takes the form x double dash of x minus k square x of x equals 0. Since this differential equation is a second order linear differential equation with constant coefficients, we write its auxiliary equation. The auxiliary equation is m square minus k square equals 0. The roots of this auxiliary equation are m equals k and m equals minus k. So, the solution of this differential equation is given by x of x equals c1 e power kx plus c2 e power minus kx. Now we substitute lambda equals k square in the second differential equation t double dash of t minus a square lambda t of t equals 0. If we substitute lambda equals k square, we obtain t double dash of t minus a square k square t of t equals 0. The corresponding auxiliary equation is m square minus a square k square equals 0. The roots are m equals ak and m equals minus ak. So, the solution of this second order linear differential equation t double dash of t minus a square k square t of t equals 0 is given by t of t equals C1 e power akt plus C2 e power minus akt. So we have found the values of x of x and t of t. In this case, x of x equals C1 e power kx plus C2 e power minus kx, and t of t equals C3 e power akt plus C4 e power minus akt. If we substitute these values in the general solution, u of x comma t equals x of x times t of t, we obtain u of x comma t equals C1 e power kx plus C2 e power minus kx times C3 e power akt plus C4 e power minus akt. We can multiply the RHS and after taking some other constants, we can rearrange this solution. Now we have to take case 3. In case 3, we have to suppose that lambda is negative. Since lambda less than 0, we can take lambda equals minus k square, where k is a real number. Now we substitute lambda equals minus k square in our two differential equations, x double dash of x minus lambda x of x equals 0 and t double dash of t minus a square lambda t of t equals 0. If we substitute lambda equals minus k square in the first differential equation, x double dash of x minus lambda x of x equals 0, we obtain x double dash of x plus k square x of x equals 0, because it is a second order linear homogeneous differential equation. We write its auxiliary equation. The auxiliary equation is m square plus k square equals 0. The roots of this auxiliary equation are m equals ki and m equals minus ki. Because the roots are imaginary, we can write the solution of the first differential equation, x double dash of x plus k square x of x equals 0, as follows. X of x equals c1 cos kx plus c2 sin kx, where c1 and c2 are arbitrary constants. Now we substitute lambda equals minus k square in our second differential equation, t double dash of t minus a square lambda t of t equals 0. Then we obtain t double dash of t minus a square k square t of t equals 0. The corresponding auxiliary equation is m square plus a square k square equals 0. The roots of this auxiliary equation are m equals plus aki and m equals minus aki. Since the roots are imaginary, we can write the solution of our second order linear homogeneous differential equation, t double dash of t plus a square k square t of t equals 0, as t of t equals c3 cos akt plus c4 sin akt. So we have found the values of x of x and t of t. In this case 3, x of x equals c1 cos kx plus c2 sin kx, and t of t equals c3 cos akt plus c4 sin akt. We substitute these values of the functions x of x and t of t in the general solution, u of x comma t equals x of x times T of t of our one-dimensional wave equation. Then the general solution becomes u of x comma t equals c1 cos kx plus c2 sin kx times c3 cos akt plus c4 sin akt. We can multiply on the right hand side and we replace the constants. Then we obtain u of x comma t equals a cos kx cos akt plus b cos kx sin akt plus c sin kx cos akt plus d sin kx sin akt. The solution is a very important solution in this case. So in this case, by supposing lambda is negative, we have shown that u of x comma t is equal to a cos kx cos akt plus b cos kx sin akt plus c sin kx cos akt plus d sin kx sin akt, where a, b, c, d are arbitrary constants. Thus, we have solved the one-dimensional wave equation u sub tt equals a square u sub xx in 3 cases depending on the lambda values. Remember that we have not considered any boundary conditions in solving this wave equation. If boundary conditions are given, by applying those boundary conditions, we can find out the arbitrary constants from the solutions in the 3 cases. Thus, we have solved a one-dimensional wave equation. In this present lecture, we have solved one-dimensional heat equation and one-dimensional wave equation. To solve these linear second order PDEs, we have used the method of separation of variables. For further queries, you can contact me through email. Thanks for watching.